cloud. Okay, so today we're covering lesson 3, which covers chemical bonding. Now, chemical bonding is when takes place when chemical compounds are formed when 2 or more atoms come together and are joined together. And in this lesson, we're going to review some of the basic chemical bonding that you learned in your grade 11 chemistry. And then we're also going to build upon that knowledge using some of the things that we learned in our previous lesson on quantum mechanics. Some of the key concepts in today's lesson is to be able to predict the molecular shape of some simple molecules and ions using the Vesper model theory, and to use the appropriate scientific vocabulary to talk about ideas that are related to structure and bonding. So, and some of these vocabularies are things like orbitals and, oh, I'm sorry, this is a slide from a previous lesson, but to be able to also predict the polarity of various substances using molecular shape and electronegativity. So first, let's talk about ionic and covalent bonding and the octet rule. Now, the octet rule is something that some of you may have heard about and may be aware of. And so atoms form bonds to become more chemically stable. And the most chemically stable elements on the periodic table are the noble gases. And we know this because they're extremely unreactive and they don't tend to form compounds with other atoms. That's because they have complete outer shell of electrons. And following this octet rule results in completely filled s and p orbitals. So if you recall from our previous lesson, s and p orbitals, the octet rule results in completely filled s orbitals and p orbitals in the atom's outermost energy level. So atoms bond or react in order to achieve this this octet configuration, to achieve the same electron configuration as noble gases have, as these unreactive noble gases have. And this rule is called the octet rule because all noble gases, except for helium, of course, have 8 valence electrons. Now, there are some exceptions to this octet rule, I must say, and if we have some time, we can talk about it at the end of our lesson. But generally, low atomic weight elements, like the first 20 or so elements of the periodic table, are very likely to adhere to this octet rule. And atoms that have an identical electron configuration are said to be isoelectronic. So an atom that has lost or gained an electron to become stable is referred to as an ion. And an atom that has lost an electron has a positive charge, and it's referred to as a cation. And an atom that has gained an electron and has a negative charge is referred to as an anion. So another way to draw atoms and ions is to use Lewis structures. Lewis structures show only the valence electrons that the element has. So in this table here, this table shows the Lewis structure for the first 20 or so elements of the periodic table. And what I want you to notice here is the full periodic table showing the electron configuration of the elements. What I want you to notice here is that the group number, which is a number on the vertical column, so this is group 1, group 2, group 3, 4, 5, 6, 7, and 8, the group number indicates how many valence electrons the atom has. Now recall that the valence shell is the outermost occupied shell. So looking at the periodic table, the period number or the horizontal rows is the principal quantum number n of the electrons in the valence shell. And the group number, the vertical columns, indicates how many electrons the atom has. So let's look at, for example, two examples here. Let's look at lithium. Now lithium, here it is. It belongs in group 1. It's element number 3, which means it has 3 protons and therefore 3 electrons. And its electron configuration in its outermost shell is 2s1. So 2s1, that means that it has 1 electron in its outermost s orbital, 1 valence electron. We call this the valence electron, that how many electrons there are in the outermost shell. So lithium belongs in group 1 and has a valence electron of 1, and so does sodium, and so do all the elements that are in group 1. So sodium and potassium and so on and so forth. We don't really need to worry too much about these higher numbered elements. And an element like fluorine, for example, belongs in group number 7, and it has 7 valence electrons, just like chlorine and just like bromine. So these are all group 7 elements and have 7 valence electrons, 7 electrons in their outermost shell. So to draw Lewis structures, Lewis diagrams, there's a few simple steps to follow. It's very, very easy. The first thing you do is you write the atomic symbol of the element. So for chlorine, you write its symbol, Cl. This represents the atomic nucleus, and you can imagine it to have 4 sides. So 1 side, 2, 3, and 4 sides to this. Just imagine that. Then we place these valence electrons, 1 in each side. So we fill up 1, 2, 3, 4. And then if we have more electrons, then we start pairing them up if necessary. So chlorine has got 7 electrons. So first we start by doing 1, 2, 3, 4, and then we start pairing them up 5, 6, 7. And in this example, this is what the Lewis structure for chlorine atom would look like. So Lewis structures and quantum mechanics are very much related, as we started to see. There is a relationship between atomic bonding, between atomic theories and bonding theories that you learned in your previous year. So an atom tends to lose electrons if it has between 1 and 4 electrons at its outermost orbit. An example of this would be magnesium, for example. So when an atom donates these free electrons, it then has positive valency. For example, magnesium has 2 electrons. So if we go back and look at our periodic table and find magnesium, there it is, as expected in group number 2. It has 2 electrons in its outermost orbital. 3s2 is its outermost orbital. So these 2 electrons, it's very likely to donate. Magnesium donates these 2 electrons, and therefore it will have a positive charge and become magnesium plus 2. An atom like nitrogen, for example, will gain electrons if it has somewhere between 4 and 7 electrons in its outermost orbit. In this case, it would be easier to accept electrons than to donate them. For example, nitrogen will gain 3 electrons to arrive at its stable octet. And one like sulfur, for example, it has room for 2 electrons. It will gain 2 electrons to arrive at its stable octet. It has space for 2 more electrons in its 3p orbital here. And over here, you can see that nitrogen in its 2p orbital has got space for 3 more electrons. So it will tend to gain electrons. Whereas in one like magnesium, where it has 2 electrons in its outermost orbital, in the 3s orbital, this is very likely to be able to donate these 2 electrons to another atom, which requires 2 electrons to achieve a stable octet. So the octet rule, as you can see, comes from the maximum number of having 2 electrons in the s orbital and 6 electrons in the p orbitals. As you can see down here in the electron configuration of some of these example elements that we've shown here in this table. So there is a correlation between the electron configuration, this atomic structure of structure of the electrons, and the way these elements will tend to form bonds, a correlation between atomic and bonding theories. And you can practice some of these by attempting some of these support questions. I, again, highly emphasize that these support questions are here for you to practice in order to really master the material that we're covering during these lessons. And I highly encourage you to answer all of these. And if you run into any trouble, please don't hesitate to reach out to me and ask. You can ask through an email, or we can talk about it in the next class. You can always ask, and we can talk about it a few minutes before class begins, or after the class is finished, we can talk about it. So please try all support questions. And if you have any problems, don't hesitate and don't fall behind. This is a pretty fast moving course. These support questions are very important. So as we were saying, the arrangement of electrons and the number of electrons in the outermost orbital of elements have a lot to do with how they will bond. So bonds within molecules or intramolecular bonds take place when an ion, for example, loses or gains an electrons, and it is forming an ion. An atom always loses or gains an electron in partnership with another atom to form this kind of a chemical bond. There are 3 types of intramolecular bonds that exist within a molecule, which we will explore in this lesson. And these types of intramolecular bonds are ionic bonds, covalent bonds, and polar covalent bonds. So the way we can think of or predict how these, what type of bond will be formed will be by our knowledge of the electronegativity of elements. Now, electronegativity is a measure of how strongly an atom attracts a pair of electrons that it shares with another atom in a covalent bond. And atoms of different elements have different electronegativities. And we can see a trend in electronegativity values on the periodic table. And these electronegativity values were determined by Linus Pauling. And they generally tend to increase across the periods. So as you go from left to right, the elements become more electronegative. There is an increasing electronegativity as you go across the periods. And there is a decrease in electronegativity as you go down a group. So there is that trend that as you go to this upper right corner, you have the more electronegative elements here. So how does that help us? So let's consider this hypothetical molecule made up of 2 atoms. If these 2 atoms have identical electronegativities, such as is the case, for example, in a hydrogen molecule, H2, you have 2 atoms of hydrogen, identical electronegativities, then they will share their bonding electrons equally. So here I've shown you in general, when you have an electronegativity difference, which in my notes I denote as delta En, change in electronegativity or difference in electronegativity between two atoms, when it's very small or zero, as is the case with this H2 molecule, the covalent bond between them is non-polar. It doesn't have a polarity. It's equally shared amongst the two. Neither one of these is having a stronger or weaker pull on the electrons. Neither one of them is attracting the electrons more closely. So, but when you have an electronegativity difference between two atoms, and when this electronegativity difference is relatively large, such as is the case in the molecule of hydrogen fluoride, HF here, then the covalent bond between the hydrogen and the fluoride will have a polarity. There will be a polarity in this bond, and there will be a charge distribution as well. No longer are the electrons equally shared, and the more electronegative atom, the fluorine, which if you recall in our periodic table, is actually very electronegative. It's right here at the very top right corner, the most electronegative. It's very electronegative. Will have a stronger attraction for these electrons. Electronegativity is a measure of how strongly the atom attracts a pair of electrons it shares with another atom in a covalent bond. So this fluorine tends to have a stronger pull on the electrons that are shared between these two atoms in the covalent bond. And we denote this polarity of this polar covalent bond by using this these symbols, the deltas of plus and minus, so that the hydrogen will have an overall polarity of being more positive, and the fluorine will have a more a negative polarity to it, so that the electrons are pulled more in this direction. And this can also be shown by using an arrow pointing towards the more electronegative atom and putting a plus at the end of the lesser electronegative, at the positive end of the polar covalent bond. So in order to predict what type of bond is going to be formed, we can use electronegativity, or the difference in the electronegativity of the two atoms. So in general, there's tables that show the electronegativity values for different elements, metals, non-metals, what have you. And if you see that the difference in the electronegativity between two atoms that are in a bond together is in the range of 0 to 0.5, then that type of bond is very likely to be a non-polar covalent bond, so just a regular covalent bond. Now, as you get an increase in bond polarity, you see a greater electronegativity difference. So if the electronegativity difference between the two atoms in the bond falls somewhere between 0.5 and 1.7, then this is probably going to be a polar covalent bond. This bond will fall in this region, and it will fall under a polar covalent bond. This is also summarized here in this table on the right. Now, finally, if there is a very large difference in the electronegativity between the two atoms, such as values, difference in electronegativity of greater than 1.7, then you will have an ionic bond type. And the character of that bond will be ionic. So the difference in the electronegativity between the atoms involved in bonding will determine the character of the chemical bond, as summarized in this table here. Let's look at an example together. to determine the elements, if the elements would form ionic, covalent, or polar covalent bonds with each other. For example, let's look at this substance, this potassium fluoride. So the electronegativity difference in potassium is 0.4, sorry, the electronegativity value is 0.8. The electronegativity value in fluorine is 4. The difference between them is 3.2. So, and if you recall, looking back at our table, 3.2 is a very large electronegativity difference, certainly greater than 1.7. So as you can guess, this would be an ionic type of bond. Let's look at O2. O2, well, two elements of oxygen, as you would suspect, will have identical electronegativities. The difference between them would be a difference in electronegativity of 0. And so the electrons would be equally shared amongst the two atoms of oxygen, and the bond would have a covalent character. It would be a covalent bond with no polarity to it. In a substance such as hydrogen chloride, where one element has electronegativity of 2.1 and another one has an electronegativity of 3. So hydrogen will have 2.1 and chloride, the chlorine will have an electronegativity of 3. So you can find these values on electronegativity tables. You just look it up. Hydrogen is 2.1 and chlorine is 3. So the difference between these two electronegativity values, you subtract them, the difference is 0.9. Now 0.9 is not such a huge difference in electronegativity. It's not greater than 1.7, but and it is so it would be an ionic bond. Sorry, it would be a polar covalent bond, excuse me. It would be a polar covalent bond. It would be somewhere in between this range of 0.5. It's certainly greater than 0.5, and it's not as big as 1.7, so it falls somewhere in the middle here, and this would be a polar covalent bond here. Polar covalent bond. So ionic bonding, let's look at that in closer detail. So ionic bonding was where the electronegativity difference was going to be very high. Ionic bonding usually takes place between when you have metals and non-metals. And the electrons are transferred from one of the atoms to the other one to form oppositely charged ions. So this is a complete transfer of electrons. It's donated. It's not a shared electron, as is the case in the covalent bonds, but it's a transfer of electrons. So one atom loses its electrons and develops a plus charge, and this would be referred to as the cation, and the other atom gains electrons. It has a negative charge, overall charge, and is referred to as the anion. For example, let's look at an example, potassium and fluorine. So using Lewis structures, we will draw the formation of a bond between potassium and fluorine. So step 1 is to write out the correct number of valence electrons for each atom. So we write down potassium and fluorine. So potassium belongs to group 1, right here. Oh, better. Yeah, right here. Potassium belongs to group 1. It has 4s1, 1 electron in its outermost orbital. And then fluorine belongs to group 7. It has 2s2 and 2p5. So altogether 7 electron in its outermost orbital. So let's go back to that slide. So we write them exactly like that. We write the symbol 1 electron for this, and 7 electrons around the fluorine, starting with 1 electron on this side. Once all 4 sides have a single electron, then we can start pairing them up in this way. So we then take a look at the valence electron. To get to a full octet, to the full stable octet, potassium will have to lose one of its electrons in a way, and then fluorine will gain this electron. So then potassium will develop a stable octet, while fluorine also develops a stable octet. Potassium loses 1 valence electron, becoming a cation with a charge of +1. And fluorine gains a valence electron, becoming an anion with a charge of -1. So notice that the ions are written now with a square bracket around them and an overall charge indicated on the upper right-hand corner. So here it is, the potassium has lost its electron, developed a charge of +1, it's become a cation, and fluorine has gained an electron right there that potassium donated to it. And we draw the square brackets around it, and we give it an overall charge of -1. It has now become an anion. So when you also, I just wanted to point out that when you're naming ionic compounds, the way to name them is to name the cation first. In this case, the cation is the potassium, and then the anion. So the potassium first, and then the fluorine. And you put the ending of "ide" onto your anion, so that this compound becomes potassium fluoride. So potassium and fluorine form the compound potassium fluoride. The positive potassium cation is attracted to the negative fluorine anion, and this is what forms the ionic bond between the potassium and the fluorine. It forms potassium fluoride. So let's take another look at ionic bonding. Let's look at another example, magnesium and nitrogen. So again, using Lewis structures, we draw the formation of the bond between the magnesium and the nitrogen. So magnesium belongs to group 2. It has 2 electrons in its outermost orbital, and nitrogen has got 5. 1, 2, 3, 4, 5. And it belongs to group 5. So let's go take a look and just confirm that on the periodic table. So yeah, there's nitrogen, and there is magnesium. So we draw the magnesium and the nitrogen with their respective 2 electrons and 5 electrons. In this case, magnesium is more likely to lose its 2 electrons, and the nitrogen will gain 2 electrons. But this does not balance, because then nitrogen still doesn't have a stable octet. So we need 3 magnesium atoms and 2 nitrogen atoms to make this balance work out. So the transfer of electrons from magnesium in nitrogen, it is such that you need 3 magnesiums donating to 2 nitrogens, as shown in this picture here. So if you follow the arrows, this electron, you can imagine, will pair up with this one here, this electron with this one. Then another magnesium comes in with its electron and completing this nitrogen, but it still has 1 more that it will share with, it will donate, rather, transfer to this nitrogen. And then finally, a 3rd magnesium will donate its 2 electrons, and you will have 3 magnesiums with an overall charge of +2 on them, forming an ionic bond with 2 nitrogens with an overall charge of -3 on them. They each have lost 2 electrons, and each have gained 3 electrons, making this a +2 and a -3. So we can summarize this by drawing brackets around it, and on the upper right corner, we indicate the charges of the ions. And on the lower right, we write the number of ions that are involved in this ionic bond. In this case, 3 magnesiums and 2 nitrogens. And again, how do we name this compound? We name the magnesium first and the nitrogen next. So the cation first, and then the anion, and then the ending for the anion becomes an ide. So magnesium nitride. There are some support questions for you to practice with and to work through. Does anybody have any questions so far? Was everything clear in how you would go about looking at ionic bonding and how you would represent them in a Lewis diagram? Judy and Sasan, are you guys feeling like you understand this?
Yes.
Yes, Judy?
Yes.
Okay, perfect. Okay, so now let's look at what is the situation when you want to draw a Lewis structure for polyatomic ions. So polyatomic ions, like we were describing, are ions that are composed of more than one atom, and that's the term polyatomic. They are groups of atoms that tend to stay together and carry an overall ionic charge. For example, nitrate, the ion formula would be NO3 minus. The ionic charge is -1. Hydroxide, OH minus, charge is -1. Many, many examples. Sulfate, SO4 -2. Oh, I should correct this right now. So I will correct these before I post these for you. These are, I apologize, the fonts got a bit mixed up. Okay, yeah, same with this phosphate here. PO4, 3 minus. With an ionic charge of -3. So drawing Lewis structures for these polyatomic ions can be a bit tricky, but there are some general rules that we'll discuss that will help us out. So for example, if we were asked to draw the Lewis structure for nitrate, NO3 minus. So first of all, we want to arrange the atoms in a symmetric way around the central atom. Now, which one is the central atom? You might be wondering. Usually, it's the one that's listed first. And it's usually singular. It's the one that there's only one of, as opposed to 3 oxygens, there's only 1 nitrogen. And typically, this central atom won't be a hydrogen or an oxygen, usually. So in this case, nitrogen would be our central atom. So then we add up the number of valence electrons available in each of the atoms. And this was the total number of electrons, or dots as we draw them in the Lewis diagram, in our Lewis structure. Then we have to add 1 extra electron for each unit of negative charge. So for example, we would have to add 1 extra electron because it has an overall charge of -1. It has received an electron from somewhere. Or we would have to subtract 1 electron for each unit of positive charge. If it was a compound that had a positive charge, we would remember to subtract. So what do we mean by that? For example, you have 1 nitrogen atom. So nitrogen has 5 electrons. So 1 set of 5 electrons is 5 electrons. Then we have 3 oxygen atoms. So 3 times 6 electrons, because oxygen has 6 electrons, that's 18 electrons, right? Then we have this -1 charge up here. So we add 1 electron to account for that. We sum it all up, and that is a total of 24 electrons that we have to take into account when drawing this Lewis structure for this polyatomic ion. So we start with 24 electrons, and we see that, okay, how are we gonna arrange these 3 oxygen atoms in a symmetrical way around the central atom. That's our first step is, okay, so let's put 3 around it. And we place a bonding pair of electrons between each. So there's 2 electrons for this bond, 2 electrons here, and 2 electrons here. So we've used 6 electrons out of the 24. And then we want to place the pairs of the remaining valence electrons, or even lone pairs, on the surrounding atoms, following the duet rule or the octet rule appropriately. So in this case, we have 2, 4, 6. Then we start adding more around the remaining spaces that we have around the oxygen. So we can add 6 more around each of the 3 oxygens. And if the central atom still does not have an octet, as is the case here with this nitrogen, it still doesn't have an octet, then what do? Then we move one of the lone pairs from the surrounding atoms so that we can now form a double bond or a triple bond, whatever will satisfy the octet rule for all the parties, for all the atoms that are involved. So now by having a double bond here between this nitrogen and this oxygen, everybody's happy, everybody's got a nice octet, and we draw the overall structure of the overall Lewis structure by writing the whole thing. So instead of our 2 dots, we can replace it now with a single bond. And instead of 4 dots representing 4 electrons, we can draw a double bond. We draw the structure of our polyatomic ion and put a square bracket around it, leaving the rest of these lone pair electrons out here alone, and showing the ionic charge of -1 on the top right-hand corner of the square brackets. So this is how you would write a Lewis structure for something like nitrate, for a polyatomic ion. An ion, we know it's an ion because it has a charge of -1, and we know it's polyatomic because it has multiple atoms. And this table is an example of many other polyatomic ions. So here's 3 examples of polyatomic ions that you can attempt to see how you would tackle the problem of drawing a Lewis structure for each one of these polyatomic ions here. So that covers ionic bonding. Now let's take a look at covalent bonding. So ionic bonding was a situation where there was donating of electrons, a transfer of electrons, so that magnesium will actually lose its electrons and nitrogen will gain it. In covalent bonding, nobody loses, nobody gains. There's a sharing. Covalent bond forms when 2 or more non-metals share 1 or more pairs of electrons. And these shared electrons are called bonding electron pairs because they're involved in the bond. And covalent bonds typically form between atoms of non-metal elements. So before, when we were talking about ionic bondings, it was typically between metals and non-metals, if you recall. But in covalent bonding, it's between pairs of non-metal elements. And as a result of forming these covalent bonds by sharing electrons, the atoms end up with their stable electron arrangement in their outer orbit, and that stable octet rule, and that's what noble gases have. So all atoms ultimately want to achieve that same stability that noble gases have by either transferring electrons or sharing electrons to have that stable electron arrangement in their outer orbit, that octet. So let's look at 2 hydrogen atoms, for example. and look at how they come together and form this covalent bond. So as two hydrogen atoms, when they start out, they might be sufficiently apart to have no interaction. And as they move closer together, their electron clouds attract each other's nucleus. So the electron cloud of one hydrogen atom then starts to attract the nucleus of the other hydrogen atom and vice versa. The two electron clouds and the nuclei also repel each other. And then once these repulsive and attractive forces are in balance, you have an optimum distance that achieves overall lowest energy for the system. And you have this hydrogen molecule formed, this H2 molecule formed. The interaction of the two hydrogen atoms as they move closer together is shown here in A, as I was describing. When the atoms are first far apart, they have no interaction. As the atoms begin to come closer together and interact, and finally the atoms interact to form an H2 molecule, and they're at a distance that has got the minimal energy. And it's the attractive and repulsive forces are balanced, and there is this sharing of electrons in the covalent bond, and there is now two bonding electron pairs that satisfies both hydrogen atoms. Hydrogen is the only one that doesn't require the stable octet. After all, it only has one electron, so the best it can do is achieve a two electron orbit and achieve stability in that way. So continuing with covalent bonding, let's look at an example using Bohr diagrams to draw the formation of chlorine gas, Cl2. So two elements, two atoms of chlorine forming chlorine gas, Cl2. So the chlorine atoms are held together with a covalent bond. Each chlorine atom, as you recall, has 7 electrons in its outer orbit and needs to gain just one more to become stable. It's got one opening, if you may. So two chlorine atoms can then share a pair of electrons to form a covalent bond. And each chlorine atom now would have 8 electrons in its outer orbit, which will then form a stable octet. So here here's the Bohr diagrams for chlorine. So chlorine, if we go back and look at our periodic table. So chlorine has got 17 protons, therefore 17 electrons. Its outermost shell will have only 7 electrons. Its outermost shell will have 3s2, 3p1. So let's go down to where we were looking at it. Okay. So here's chlorine with its 2, and then 8, and then 7. So altogether, 17 electrons drawn in this Bohr diagram. So this is one of the ways of you can use Bohr diagrams to help, or it's kind of summarized in a way in a Lewis diagram. When in the Lewis diagram, we only show the outermost electrons in the outermost orbital. So chlorine has got 7 over here. So you can see in the Bohr diagram, these two outer orbitals can come together and share the electrons. That way they each now have satisfied octet rule, and there's 8 electrons in each of their outer shells, which forms the stable octet. And if we want to show the same thing using Lewis structures, well, this is how you show it. It's much more simple. You write your chlorines and you put 7 dots around them to represent the 7 electrons in the outermost orbital, and or the outermost orbit. And you represent the sharing of these two electrons. Then these two come together and are shared in a covalent bond. And here are some other examples of covalently bonded molecules, such as methane, such as water. And here it is shown in the Bohr diagrams, such as ammonia, NH3. So how are these electrons shared between atoms? Valence bond theory explains why and how these electrons are shared between atoms. Valence bond theory proposes that individual atoms, each with their own orbitals and electrons, come together and form covalent bonds in a molecule. And a covalent bond between two atoms is formed when a pair of electrons is shared by the two overlapping orbitals, as we have discussed so far. And when the covalent bond forms, the lowest energy state is obtained when atomic orbitals overlap to form a new orbital with a pair of opposite spin electrons. Now, some of the key points of valence bond theory is that a half-filled orbital in one atom can overlap with another half-filled orbital of a second atom to form a new bonding orbital. The new bonding orbital will contain two electrons, each having an opposite spin, as you remember from your quantum theory. When atoms bond, they arrange in space in an arrangement that allows for maximum overlap. Now, VSEPR theory, which we will discuss next, assumes that the majority of the electron density for bonded pairs of electrons is in the vicinity of the bond. And the valence bond theory helps to explain why this assumption is justified. So these two, the VSEPR theory and valence bond theory, kind of go hand in hand. So let's take a look at valence bond theory. Let's take a look at bonding of two hydrogen atoms. So the electrons of each of the two hydrogen atoms, if you recall, are in the 1s orbital. And when these two 1s orbitals come to overlap, you get a covalent bond formation, as we looked in our slide up here. So here is the electron clouds, 1s and 1s. And in this bond, the electrons in the bonded 1s orbitals, so there's an overlap of 1s orbitals and then the covalent bonds, will have opposite spins similar to the filled atomic orbitals. So one up and one down. So the formation of a covalent bond in this elemental hydrogen, this H2, according to valence bond theory, looks something like this. When the hydrogen molecule forms, each of the 1s orbitals overlap to form this covalent bond. And in the hydrogen molecule, these electrons will have opposite spins that have a lower energy state than the separate hydrogen atom. So it's more favorable, energetically more favorable. Now, I have a couple of YouTube videos that show, and this is these, when you have two s orbitals that come together in a head-on sort of an arrangement. I mean, s orbitals are spherical, so there's no other arrangement. They come together. They form a bond called a sigma bond. And we are going to take a look at a YouTube clip that shows how these sigma bonds are formed. Let's look at one of these together. So the first one is for H2, a sigma bond, as is the case in an H2 molecule.
A sigma covalent bond is formed by the overlapping of two s orbitals, or one s and one p orbital. or two p orbitals orientated along a common axis.
Okay, so when they come together in this head-on arrangement,
S and one p orbital.
you form a sigma bond. So either when you have two s orbitals coming together or two p orbitals coming together in a head-on arrangement, or a 1s and a 1p orbital coming together, you get this sigma bond. Now, was everybody able to hear the volume on my video?
Yes.
Okay, very good. All right, so let's go back to, so yeah, there's one more that you can see. So here's an example of a sigma bond in a fluorine molecule, where you have a 2p orbital. So two of these 2p orbitals have got one electron in them each. And when they come together in a head-on arrangement, you also get a sigma bond. So let's watch this together.
Fluorine atoms have 7 electrons in the valence shell, 2 in the 2s and 5 in the 2p orbitals. The 5 2p electrons are distributed among the 3p orbitals in such a way that 2 of the orbitals are filled with paired electrons, while the third one has a single electron.
So here they're showing that this is one p orbital. So this is one dumbbell that represents one of those 2p orbitals. And there's a pair of electrons there. And here's the second of the 2p orbitals in this dumbbell here. And there's a pair of electrons there. And there's a third 2p orbitals. And that one has got just one electron in it, right?
Only the last mentioned is available for forming the covalent bond by sharing its electron with another atom. Consequently, the covalent bond can be formed by the overlapping of singly occupied p orbitals. A bond produced by such head-to-head overlapping of p orbitals is a sigma bond.
Okay, so here they were showing how in these 2p orbitals, where the 3 of them, 2 out of 3 have got 2 electrons. One of the 2p orbitals has a single electron. So this single electron in this 2p orbital from one fluorine atom can then form a sigma bond with another fluorine atom who will also have a single electron in its third 2p orbital. So these two, when they come together in a head-on arrangement in this way, so if it's the orientation is head-on in this way, the two dumbbells coming together with their heads, they form a covalent bond, and this type of bond is called a sigma bond. Okay. Now let's go back to our slides. Where am I? Where is my mouse? There we are. Okay. So right. So this is one example. If you have 1s orbitals, or if you have 2 p orbitals coming together, you can also get whether you have S and S coming together, or an S and a P, or a P and a P come together, but in an end-to-end orientation and a head-on orientation. These are the 3 ways that you can get a sigma bond, the sigma covalent bond. Now let's look at bonding in a molecule like hydrogen chloride, where you have electrons of the hydrogen atom in a 1s orbital, right? And then the electrons of the chlorine atom in the 3p orbital. So s orbital and a p orbital. When the 1s and the 3p orbitals overlap, and they will form a covalent bond. In this bond, the electrons bonded in the 1s orbital have opposite spins, similar to the filled atomic orbital. So here in the 1s orbital. That's the hydrogen. The bonding electrons will have opposite spins with lower energy states than the individual electrons. So as they bond together, they will have opposite spins. So here it is the hydrogen atom with its 1s orbital, the chlorine atom with its 3p orbital. It has only 5 electrons in there, so it has space for 1 more to become stable. They will come together and overlap, and they will form a covalent bond here. And let's look at a video that shows a similar situation. Here in this diagram, I've shown hydrogen chloride. Let's look at a video that will show us for hydrogen fluoride, what this will look like. And I think these videos show in a very nice way what is kind of sometimes hard to imagine, but when you see them in motion in video, it kind of makes it easier to wrap your head around what's happening. So next, sigma bonds in hydrogen fluoride. Let's take a look at this together.
Both hydrogen and fluorine possess a single electron, which can be shared with the other atom. They are in different orbitals, 1s in hydrogen and 2p in fluorine. But they can still overlap to form a covalent bond. The bond formed by the overlapping of s and p orbitals is a sigma bond too.
Okay, so that's another example of a sigma bond.
My job is
Oh,
to make
excuse
college easier because students have a lot of
Excuse me.
plays. Mike Harper in econ.
Molecular orbital diagram.
Both hydrogen and fluorine possess a single electron.
Sorry about that. Okay, so we looked at the example of hydrogen fluorine, very similar with hydrogen chloride, hydrogen fluoride rather, and hydrogen chloride, very similar. Now in polyatomic molecules, for example, like ammonia, you will have 1 nitrogen and 3 hydrogen atoms that would be arranged in this, what this arrangement, the geometry is called a trigonal pyramidal structure. And we will get more into that as we get more into the geometries. And the valence electron diagram of the nitrogen atom shows that it has 3 unpaired electrons in its p orbital. So each of the 3 hydrogen atoms has got 1 electron in its 1s orbital, and it's able to contribute these 1s orbital electrons to the 3 unpaired electrons from the 2p orbitals of the nitrogen atom, and to form this overlap with the 1s and the p orbitals, forming 3 covalent bonds. So here, each of these will overlap, and we will have 3 covalent bonds that will have a lower energy state than the individual atoms. So in the ammonia molecule, the bonding electrons, once they overlap, will have opposite spins and will have a lower energy state than they had when they were in their individual atoms. So that makes this bonding very favorable, the sharing of electrons. Now, in addition to sigma bonds, you can also have orbitals that, so in addition to, rather, I should say, when you have sp bonds coming together that form a sigma bond, you can also get hybrid orbitals. You may have noticed that the orbitals, when they bonded and overlapped, they changed shape. So as you saw in one of the videos where we were showing the coming together of s and a p orbital, the resulting orbital at the end actually had a different shape. So let's take a look at that. And you can see that So here, as they were coming together, here's the s orbital and the p orbital. And as they came together, if you notice the arrangement of the new sigma bond, this new orbital has a different shape. So this is called a hybrid orbital, or an sp hybrid orbital. So when you have, I'm sorry, I didn't explain that correctly. So no, sorry, that's not an sp hybrid orbital. That is just a regular sigma bond. Sorry, it has changed shape, but it's not sp orbital. So sp orbital, scratch that. Sp orbital, excuse me, is when you have s orbitals and p orbitals that are, p orbital is empty, but you get this excitation of the electrons that is then donated to the p orbitals, and then these together form a new hybrid orbital called an sp hybrid orbital with empty p orbitals and this new sp hybridized orbital. So let's look at an example of this hybridization process where you get a combination of two or more atomic orbitals to create a new orbital that is hybridized. So when you have these hybrid structure, it's a restructuring of the s and the p atomic orbitals to form a new hybrid orbital or an sp orbital. So let's take a look at that, an example of an sp hybrid orbital and then an spp or an sp2 hybrid orbital, or when you have s and 3 p's or an sp3 hybrid orbital. I've got 3 videos lined up here that show these structures very clearly. And then the 2 sp orbitals are linear. They're 180 degrees apart like this when you get these 2 new sp orbitals, or you get these 3 sp2 orbitals. They're arranged in this planar orientation with 120 degrees between them. Or you can, in the case of these 4 individual orbitals, so 1s and then 3 of these p orbitals come together to form 4 new orbitals. So 4 orbitals with a new name, sp3 orbitals, and each one of these sp orbitals is arranged in this tetrahedral fashion with 109.5 degrees in between each of these orbitals. And this is their arrangement. So we can use also this information to understand the geometry of molecules that form as a result of the hybridization of these hybrid orbitals, as a result of the hybridization of these orbitals, excuse me. So let's watch one for sp hybridization for beryllium hydroxide. Okay. BH2. Let's watch
A
this.
beryllium atom has only 2 valence electrons in its outermost electron shell. They're both situated in the 2s orbital, as this orbital has lower energy than the 2p orbitals.
So, right, so beryllium has got a 2s. So technically, it should not really want to bind with anything. It doesn't have any lone pairs of electrons, and yet it does. So let's take a look at how it is that beryllium forms compounds with other atoms.
The 2p orbitals remain empty. Since the electrons in the 2s orbital are paired, there are no single electrons to share with other atoms. Beryllium should not form any bonds. Yet many beryllium compounds are known in which beryllium forms 2 covalent bonds. Beryllium hydride, BeH2, is one of them. How can beryllium form 2 bonds? Evidently, one of the 2s electrons is excited to the 2p sublevel. In this way, single electrons are situated in 2 different atomic orbitals. They can overlap, at least in theory, with the singly occupied 1s orbitals of hydrogen atoms to form a BeH2 molecule. But if this were the case, the 2 beryllium hydrogen bonds should be different, as they would involve different beryllium orbitals. However, Experiments show that both bonds are identical.
Okay, so here they're saying that, yeah, if one of them becomes excited and is promoted to the 2p orbital, as they were showing here. So one of these 2s electrons is excited and it's promoted to the 2p orbital. So now you'll have one electron in the p orbital, one electron in the s orbital. So now technically you have two electrons alone in their orbital, which have the capacity to then overlap and share electrons and form a bond. And if this happened, then you would get two bonds. But these two bonds, as you can imagine, will have very different characters, very different natures, because one of the bonds is as a result of a 1s and a p orbital, an s and a p orbital coming together. Whereas in the other one, it's a result of an s orbital and another s coming together. So these two bonds should be a bit different. But
if this were the case, the two beryllium-hydrogen bonds should be different, as they would involve different beryllium orbitals. However, experiments show that both bonds are identical. How is that possible? The hybridization concept assumes that one 2s orbital mixes with one 2p orbital to give two identical hybrid orbitals.
So yeah, so there the hybridization says that, okay, so you have one of the electrons excited and promoted to a p orbital, but now what happens is that now you have a hybrid orbital. So instead of you having one s and one p orbital, you have two sp orbitals. So you still have two orbitals, each with a single electron in it, but it's a new kind of orbital called a hybrid orbital, an sp orbital.
Known as sp, of exactly the same energy. The hybrid orbital is unsymmetrical.
So this sp orbital has got an energy somewhere in between the 2s and the 2p. And these have the same energy.
It consists of two deformed ellipsoidal parts, a larger and a much smaller lobe. The energy of the hybrid orbital is intermediate between the energies of the mixed orbitals forming it. Hybrid orbitals repel each other, just like bonding electron pairs. In this example, they are pushed apart as far as possible to be arranged along a straight line. The overlap of two hybrid 2sp beryllium orbitals.
So here, if you can imagine, now this is the beryllium with its hybrid sp orbitals, two of them. So one on this side, one is pointing that to the other because they repel each other. If you can think of the geometry of these, sometimes you can think of it as if you had two balloons and you were trying to tie the ends of the two balloons together, they kind of stick away from each other. So if you try and tie two balloons together, you would form this sort of structure with them pointing 180 degrees apart from each other. So now each of these sp hybrid orbitals is ready to form a sigma bond with this with these hydrogen s orbitals.
With the 1s orbitals of two hydrogen atoms gives rise to two identical bonds. The beryllium hydride molecule assumes a linear shape with a bond angle of 180 degrees. Notice that valence bond theory combined with the hybridization concept gives the same shape of molecule as predicted by the VSEPR theory.
So that's the VSEPR theory that we were talking about that I will cover as we get a little bit further along into our lessons. Okay. So,
beryllium atom.
So, right. So the other kind of hybrid orbital you can have if you have SPP or SP2 orbitals, where you have an s orbital and you have two electrons in your s orbital and one electron in your p orbital, And what can happen is then this electron becomes excited and gets promoted into the second p orbital. So the difference here is that in this situation with the sp orbital, there was 2 electrons in the s and the p orbitals were completely empty. One of these electrons gets excited and is promoted. So you have this s and a single p. Together, you form 2 new hybrid orbitals or 2 sp orbitals. Here you have one of the p orbitals already has 1 electron. So when the other electron from the s orbital is excited and promoted into the other p orbital, now you have 3 orbitals with singular electrons. You have s and then p and then another p. These 3 will then combine and form a new type of orbital, 3 new orbitals that are hybrid orbitals, and these are sp2 hybrid orbitals. Let's take a look at these. And these 3 orbitals tend to arrange themselves in this planar fashion. So in the sp orbitals, 2 sp orbitals, they arrange themselves in this 180 degrees apart. Now, if you can imagine, if you had 3 balloons that you were trying to tie together, they would arrange themselves in this planar fashion. Each of them would try and point away, give each other as much space as possible. So these electrons will repel each other and try and point away as far away from each other as possible, achieving this planar arrangement, 120 degrees between each one of these hybrid orbitals. So you would get 3, 1, 2, 3 sp2 orbitals. So let's take a look at a video to show how that is. An example of that is in the ethene molecule C2H4. Let's have a look at that. And that I have here for you.
Each carbon atom in an ethene molecule is linked to 3 other atoms and is described as sp2 hybridized. For this,
so sp2 hybridized. So each carbon is bound to 3 other atoms. So it's bound to this carbon and to these 2 hydrogens. And then this carbon is bound to these 2 hydrogens and this one as well. So each one is bound to 3 different atoms. And
for this type of hybridization to occur, the carbon atom must become excited prior to bond formation. This means that one of the electrons occupying the 2s orbital jumps to a 2p orbital.
yeah, so in this case, 2 out of the p orbitals already had a single electron in it. And then the electron from the s orbital, one of the 2 electrons here, became excited and promoted to the 3rd p orbital. So now you have a total of 4 orbitals, which will now combine to form a hybrid orbital, 4 new orbitals with a new geometry. Let's take a look at that.
What follows is the combination of 1 2s orbital and 2 2p orbitals to give 3 equivalent sp2 hybrid orbitals. 3 of the 4 valence electrons of the carbon atom occupy the new sp2 orbitals, and the 4th electron remains in the 2p orbital, which was not included in the hybridization. The 3 sp2 orbitals lie in a plane and form bond angles of 120 degrees. The 2p orbital, occupied by the 1 remaining electron, is situated at right angles to the plane of the 3 sp2 orbitals.
Right. So the important thing I wanted to show you was the 3 sp2 orbitals here. In this case here. Now, if you, there's another type of orbital called the sp3 hybrid orbital, And we can take a look at sp3 hybridization in the third video here. So one more video under hybrid orbitals to watch. And that's the methane molecule.
A carbon atom has 4 valence electrons. 2 of them are paired and located in the 2s orbital, but the other 2 are unpaired, occupying 2 of the 3 available 2p orbitals. When during reaction, one s electron is excited to a p orbital, there are 4 unpaired electrons available to form covalent bonds. The single 2s and 3 2p orbitals hybridize to give 4 equivalent 2sp3 hybrid orbitals. Overlapping of the hybrid sp3 orbitals with the s orbitals of 4 hydrogen atoms produces 4 sigma bonds. The resulting methane molecule has a tetrahedral geometry. The bond angles are 109.5 degrees. The shape of the molecule is in accordance with the experimental results and the predictions from the VSEPR model.
Okay. So there, we took a look at sp hybrids, sp2 hybrids, and sp3 hybrids.
or tetrahedral hybridization.
Excuse me, one moment.
Definition.
Now let's take a look at what happens to orbitals in double bonds and triple bonds. In double bonds and triple bonds, you have 2 kinds of orbital overlaps that are possible. You can have end-to-end overlap of s orbitals and p orbitals, or hybrid orbitals, or some pair of these kind of orbitals, and this forms sigma bonds. Or you could have side-by-side overlap, which will form a different kind of a bond called a pi bond. So if the orbitals that we have talked about, either s orbitals or p orbitals, or the hybrid sp orbitals, or some combination of these 2, so sp, ss, pp, or hybrid s, hybrid p, if these come together in an end-to-end or a head-on, where the 2 dumbbell heads come together and overlap in that way, they will form a sigma bond. But if you have a side-by-side overlap of the orbitals in either the hybrid orbitals or the p orbitals, because they're dumbbell shaped, you can also approach them side by side, then they will form a different kind of a bond called a pi bond. So a double bond is one that contains 1 sigma and 1 pi bond. So let's look at the double bond in the molecule ethene. So in ethene, which we did take a look at a little bit earlier, we'll have just a partial hybridization with 3 of the new sp orbitals, as we watched in that video, and we will watch one again, and then 1 normal 2p orbital. So here in this figure, it shows sort of what are the arrangement of the 3 new sp2 orbitals. So here is each of the carbons. So 1 carbon and 2 carbon. Here's the carbons. Here's one, here's a second one. And then we said that then when one of the electrons got promoted to the sp orbital, then you formed 3 new sp2 orbitals. So this 1 balloon here, this 2nd balloon here, this 3rd balloon here, these are the 3 new sp2 orbitals that are formed around the carbon. So if you can imagine also here, there's one normal p orbital, which is shown right here. So in your mind's eye, if you can overlap this image onto this one, if you have this kind of an arrangement where you have these two bonds, these two p orbitals coming together in a sort of a side-by-side orientation, you get a pi bond shown here by this cloud. So the pi bond comes from the side-by-side approach of these p orbitals. So you get one sort of electron cloud up here and another one here. You get this sharing of these two sp orbitals. They come together to form this kind of a sigma bond here. And then you get this overlap of the 1s and the sp2, and these also form the sigma bond. But here in the middle, you have the pi bond arrangement. So let's take a look at a video that will show us two examples, one in the O2 molecule, in the oxygen molecule, and one in the ethene molecule that will show us the arrangement of how you get double bonds that have one sigma and one pi bond. Let's take a look at both of those videos at once. So bonding in the oxygen molecule.
Oxygen atoms have 6 valence electrons. 2 of them are located in the 2s orbital and 4 in the 3-2p orbital.
So here, this red cloud here in the middle is supposed to represent the s orbital. And then each of these dumbbells represents the 3p orbitals.
One of the 2p orbitals holds an electron pair, while the 2 others are occupied by single unpaired electrons. 2 oxygen atoms can form one sigma bond by head-to-head overlapping of 2 2p orbitals.
So if you have head-to-head, or end-to-end is another term that's often used, head-to-head, head-on, or end-to-end overlapping of these p orbitals, you get a sigma bond. Okay?
Notice that in this orientation, another pair of the 2 remaining 2p orbitals can overlap in a side-to-side manner. In this way, a second covalent bond is formed. This is a pi bond, since it results from the side-to-side overlapping of p orbitals.
So here, if you look at this arrangement, these two here that have now disappeared into this sigma bond.
A head-to-head overlapping of 2 2p orbitals.
And then there is these other p orbitals that are coming side to side. And when they're side to side arrangement like this, then they will form a pi bond, as is shown here in this picture. So that there, and both of them together are a pi bond. And when you have a pi and a sigma bond together, that makes it a double bond.
In this way, a second covalent bond is formed. This is a pi bond, since it results from the side-to-side overlapping of p orbitals.
So one of the covalent bonds in the double bond is a sigma, and the other covalent bond in a double bond is a pi bond. And together they form the double bond.
The oxygen atoms are bonded together by a double bond in the oxygen molecule. The double bond consists of one sigma bond and one pi bond.
Right. Let's look at the same example in a different molecule, ethene, just to sort of make it more clear for us.
In the ethene molecule, carbon forms bonds by using sp2 hybridization. sp2 hybrid orbitals are formed from 2s and 2p orbitals. This leaves 1p orbital unhybridized. The hybrid orbitals lie in one plane, directed towards the corners of an equilateral triangle. The remaining p orbital is perpendicular to this plane. Each of the 4 orbitals is occupied by a single electron. Head-to-head overlap of the sp2 orbitals of 2 carbon atoms gives rise to a carbon-carbon sigma bond. 2 carbon atoms gives rise to a...
So here is one carbon, here's another carbon, and they have these 3 sp2 hybrid orbitals, and then they have their one normal regular p orbital arranged in this way, perpendicular to the plane of these hybrid orbitals. And as they approach each other to form a bond, the hybrid sp2 orbitals form a sigma bond.
A carbon-carbon sigma bond. The remaining sp2 orbitals overlap with the 4 hydrogen 1s orbitals to form 4 sigma bonds.
So here is one bond, a single bond between carbon and hydrogen, and you can see the single bonds between carbon and hydrogen in the other ones. And now so far we have just the one single bond between the 2 carbons. But wait, there is also this p orbital here still. Each of them still has this p orbital, but they are not oriented in a head-to-head fashion like these were. The dumbbell heads aren't coming together, the ends of the balloons. They are more in a side-by-side or kind of like a parallel kind of an approach. And when it's that situation, they form what's called a pi bond.
In this arrangement, the remaining unhybridized p orbitals of the carbon atoms are close and parallel to each other. They can overlap in a side-to-side manner to give the additional p bond between the carbon atoms. The carbon atoms in ethene are linked by a double bond composed of 1 sigma bond and 1 p bond.
That is actually a pi bond. I think it's more a British way of calling it p, but the correct way of saying it for us would be a pi bond.
If we try to rotate one CH2 group about the other along the axis of the carbon-carbon bond, one of the p orbitals would also rotate. As a result, the p orbitals of both carbon atoms would not remain parallel to each other. Rotation would require the breaking of the p bond. For this reason, rotation around the double bond is restricted and the ethene molecule is planar, with all bond angles close to 120 degrees. Notice that the sp2 hybridization concept explains not only the geometry around each carbon atom in ethene, but it predicts the planarity of the molecule too.
New Kashi soft baked cereal bars.
Right. Okay, so that was us watching what was the situation in a double bond. So here's an example. What are the bonding orbitals in a BF3 molecule? So the solution, let's talk about it. Boron has a valence of +3 and fluorine is -1. If we write the electron configuration of boron, focusing on the valence electron orbitals, in this case, we see that the 2s orbital has 2 electrons, and the p orbital, the 2p orbitals, has just 1 electron. In this case, one of the 2s electrons can be promoted or excited to occupy a higher energy level to go into an empty 2p orbital. And by promoting this s electron to an empty p orbital, there are 1 s orbitals and 2 p orbitals available for hybridization, a total of 3 identical sp2, i.e. one of them is an s and 2 of them is a p, sp2 orbitals are formed, and therefore the hybridization here is sp2. And there's another video here which we can watch together very quickly. I know you probably are thinking you're I think these videos are very helpful because they show exactly what's happening.
A boron atom has 3 valence electrons. 2 of them are paired and are situated in the 2s orbital, while the remaining one is in a 2p orbital. In the excited state, one 2s electron is transferred to one of the empty 2p orbitals. Mixing of the single 2s with the two 2p orbitals yields 3 sp2 orbitals. Notice that they are somewhat slimmer, as the contribution of the p orbitals is larger. Their mutual repulsion positions the hybrid orbitals in such a way that their larger lobes point towards the corners of an equilateral triangle.
And that accounts for the orientation or the geometry around a boron atom and how it will form bonds with other molecules.
The overlap of the sp2 orbitals of the boron atom with the p orbitals of 3 fluorine atoms produces 3 boron-fluorine sigma bonds.
Right, because these orbitals came together in that end-to-end fashion. That end-to-end fashion results in a sigma bond. If they were to come together in an orientation that was side by side or parallel, it would be a pi bond. But in this case, they come together in an end-to-end fashion, forming this sigma bond.
The molecule formed has trigonal geometry, and the bond angles are 120 degrees.
Okay. Now you might ask yourself, what is the case with triple bonds? How are they formed? So in triple bonds, one example of a triple bond would be the acetylene or the ethene molecule, C2H2, where you have 2 carbons joined by a triple bond, each of them forming a single bond with a hydrogen. So in this case, you have the promotion, the excitation of one of the electrons from the 2s into the 2p orbitals, going to give you this 2s with just one single electron, and then you have 3 p orbitals, each with a single electron, with 3 electrons across. And together you get 2 hybrids of sp, and you get 2 normal p electrons here. So in this case, you got 2 p hybridized orbitals from this pair here, and then these 2 pair just stay as p orbitals. And so yeah, 2 hybridized and 2 unhybridized orbitals are formed. So let's take a look and see what this looks like in the case of a molecule such as N2. And what does the triple bond look like in that situation? And again, we can look at it in the case of ethene and see what does that look like in that situation. So I've got 2 more videos, and I think that might be the end of videos, and we will wrap things up, okay?
Nitrogen also exists as diatomic molecules. Since every nitrogen atom has 5 valence electrons, they both share 3 of them when combining with each other. They form a triple bond. In the nitrogen molecule, both atoms have the stable electron configuration of neon.
Actually, maybe that one wasn't such a great video to show that concept. Let's take a look at this one. Actually, this one might, yes, this is the one. Sorry.
The ethene molecule contains a triple carbon-carbon bond in which both carbon atoms are sp hybridized. The hybridization of one 2s orbital and one 2p orbital produces two sp hybrid orbitals with two free unhybridized 2p orbitals. One sp hybrid orbital overlaps head-to-head with a similar sp orbital of the second carbon atom, thus forming a sigma bond. Two other sigma bonds are formed because of the other sp orbital of each atom overlapping the 1s orbital of a hydrogen atom. Unhybridized p orbitals are perpendicular to each other and to the axis of the sp orbitals. These unhybridized orbitals can overlap side to side to form two pi bonds with a cylindrically shaped electron cloud around the axis of the atoms. The triple bond in ethene consists of one sigma bond and two pi bonds.
So one sigma bond and two pi bonds, as you could see, because there were a total of two more sets of pi bonds coming from each carbon. And because of their perpendicular arrangement, their perpendicular approach, they formed pi bonds. So one and then two. And these two, you can see here, and then another one perpendicular to it. So two pi bonds and a sigma bond represents the triple bond. So because these two pi bonds are in this arrangement with each other, the distribution of the electron is around this triple bond is cylindrical.
Can overlap around the axis of the atoms. The triple bond in ethene consists of one sigma bond and two pi bonds. The ethene molecule has a linear shape.
All right. There's some support questions for you to practice with. I encourage you to do it. Now let's talk a little bit about that VSEPR model, the valence shell electron pair repulsion model. So one of the more important properties of any molecule is its shape. So it's important to know what is the shape of a molecule if we're to understand how it's going to participate in reactions. And as such, we want to have a way of being able to predict the geometry of these compounds and the shape of these compounds. So some of the underlying assumptions made by this VSEPR model are that atoms in the molecule are bound together by electron pairs. These are called bonding pairs, and more than one set of bonding pairs of electrons can bind any two atoms together. So you can have multiple bondings. Some atoms in a molecule may also possess pairs of electrons that are not involved in bonding. These are called lone pairs. But the bonding pairs and the lone pairs around any particular atom in a molecule adopt positions in which their mutual interactions are minimized. And if you can think of it, the logic here is simple. Electron pairs are negative and they will get as far away from each other as possible because of their repulsive forces. So they will arrange themselves in a way that they are pointed as far away from each other as possible. Lone pairs tend to occupy more space than bonding pairs, and double bonds occupy more space than single bonds. So these are the assumptions made by the VSEPR method. Let's take a look at how we can use this. So using this VSEPR theory, let's look at an example. And there's this table here that will help guide us. So we can be asked the question, what is the shape of beryllium hydride, BeH2? So first of all, we will draw the Lewis structure. And so there'll be a single bond between the hydrogen and the beryllium, and they'd be pointed in this 180 degrees apart. But how do we know it's going to be there? If we consider that the central atom beryllium has two bonding pairs and no lone pairs, so its general formula would be of AX2. So the A would represent the beryllium, and then two other another one. So the X would be the hydrogens. And it would be considered linear. How do we know that? We know that by sort of referring to this table that guide us. If the general formula is AX2, you have two pairs, two bonding pairs. You have no lone pairs, and you have a total of 2 pairs forming a linear geometry. And the shape would be like this. And examples of this is this beryllium hydride, BeH2, or other molecules such as CO2, CS2. These would all adopt this linear geometry, and that would come from this general formula of AX2. Let's look at another example. Let's predict the shape of a sulfate ion, SO4 minus 2. Here, the central atom sulfur has got 6 valence electrons, plus the 2 additional electrons totaling 8. This gives 4 bonding pairs and no lone pairs. So the general formula, as you can see just by looking at the formula, is AX4. And if you look at AX4, it forms 4 bonding pairs and no lone pairs. So here would be the sulfur atom represented by the A here in this diagram. And the oxygens would be where the X's are, held by 4 bonds. And these would be arranged in a tetrahedral manner. Each of them would be pointed away from each other by 109.5 degrees. So you can use this chart, and other examples of this would be CH4, SiH4 with silicon with 4 hydrogens that would be bonded in the same tetrahedral geometry. And say you have a molecule that has a lone pair, such as ammonia here, NH3. So each of the hydrogens would be bound to the nitrogen in a pyramidal fashion. And then there would be a lone pair up here. And that lone pair occupies more space than the bonded pair. So it would have a tendency to repel these other electrons to point a little bit further down and away from it, giving this molecule this overall pyramidal type of geometry. There's other molecules that may have a V-shaped geometry, such as water, where you would have the oxygen and then the two hydrogens. And in this case, you would have 2 lone pair electrons, and they would overall give this molecule a V-shaped arrangement. And then another linear shaped molecule would be an example of hydrogen chloride or bromine fluoride. Those would all give this sort of AX linear shape, as opposed to this AX2, where you would get also a linear shape, but different arrangements slightly. So then there's some support questions for you to use your Lewis structures and your Vesper theory to try and predict the shapes of some of these molecules. A very useful exercise to go through. See if you can figure them all out or if you run into problems. So far, okay, so we've covered covalent bonds, we've covered ionic bonds. Now the third type of bond that we were going to discuss in this lesson, polar covalent bond. So a polar covalent intramolecular bond, so where the bonds within the molecule have some polarity, there is not equal sharing of electrons amongst them. There's some of the atoms tend to have a greater attraction, a greater pull on these electrons. So there is unequal sharing between these valence electrons that results in a dipole at the ends. And some of the ends would be slightly more positive or slightly more negative. And the dipoles are given this symbol of this lowercase Greek delta, with either a minus for the more negative ends, or the more positive part of the molecule might get a delta plus. So let's go through one example where you have to draw the polar bond formed in a molecule of carbon tetrachloride. So CCl4 between the elements of carbon and chlorine, 1 carbon, 4 chlorine. So we look at the electronegativity table first and try and decide what kind of a bond this is. And we can see that there's electronegativity of 3 and for chlorine and 2.5 for the carbon. The difference in the electronegativity, the delta En, is 0.5. So the intramolecular bond would be considered to be polar covalent. We get this by referring to that slide, that table that I showed you much earlier in the lecture. So this one. So if the delta En is 0.5 or less, you get a polar covalent bond. So let's go back to our example. No, polar covalent bonds. And the intramolecular bond is considered a polar covalent. And since the chlorine has a higher electronegativity, right? Chlorine has got 3 versus the carbon being 0.25. This has the higher electronegativity here. The electrons would be pulled closer to the chlorine's atom molecule. Chlorine has a greater pull on the electrons that are in this bond. So this makes the chlorine ends, or the dipoles at these ends, slightly more negative, and we show it by putting this symbol on the chlorine ends of the molecule. In a similar way, the electrons are farther away from the carbon nucleus. They're being drawn more towards chlorine, so therefore the carbon will have a slightly more positive charge, a positive dipole here at this end of this bond. So these bonds between each of these each of this carbon and chlorine bonds here are polar. They have a dipole. They have a dipole where the electrons are drawn more to the chlorine ends. So covalent bonds, as we've been talking, can be both polar or non-polar, but the polarity of the molecule as a whole depends on both the polarity of the bonds and also the overall molecular shape. So if the molecule is symmetrical, symmetrical molecules produce non-polar molecules, whether or not the bonds are polar. But if you have an asymmetric molecule, if there's no symmetry, then the molecules produce non-polar molecules if the bonds are all non-polar. Let's talk about this so that it makes sense. Let's look at an example of ammonia, NH3. And you're asked to predict the polarity of ammonia and include your reasoning behind it. So first we have to draw the Lewis diagram. Next, we have to check the electronegativities of the atoms involved. Nitrogen has an electronegativity of 3, hydrogen 2.1. This difference is 0.9. So if we look at our electronegativity difference table, the guide, this would make the hydrogen end a little bit more positive and the nitrogen end negative. So this would, so this difference, first of all, makes it fall into the region of polar covalent bonds. And then because we know that the nitrogen end has got a greater electronegativity than the hydrogen ends, we know that the hydrogen ends would be slightly positive, the nitrogen ends would be slightly negative. Now we must also consider the symmetry, if there's any symmetry around here, any sort of a geometry. But because ammonia has got that AX3 plus it has that lone pair up there, it's not a symmetrical molecule. So these bonds will be polar and the molecule overall will be polar. So it would be more positive on this end and more negative on this end. Because of the electronegativity of the nitrogen, it would have a greater pull of the electrons from these bonds. And then the further position of this lone pair of electrons will also make this region here more negative. And so this would not be overall, it would not be a polar molecule. Overall the molecule would be polar. The bonds are polar and overall the molecule is polar. And we base that on the determination of the polarity of the bonds and also looking at the the symmetry and the geometry of how these bonds are arranged with respect to each other. So we have a few minutes at the end of our lessons here. I can take these few minutes to talk a little bit about when I mentioned the octet rule, and I said there are some exceptions to the octet rule, which you should just be aware of. There's 3 main exceptions to the octet rule that I just wanted to share with you, just so that you have an awareness of these situations. One of them is that molecules with central atoms that are surrounded by fewer than 8 electrons, those are not following the octet rule. For example, in one of the examples we were looking at, the boron trifluoride, the BF3. So boron, if you count the number of electrons around it in this Lewis diagram, you can see that it has 2, 4, 6. It doesn't have 8 electrons. So then this is not following an octet rule. Each of the fluorines has got an octet around it, but boron does not. So therefore, the reactivity of this boron tetrafluoride with other electron-rich molecules, such as water or ammonia here in this diagram, takes place because boron atom is electron deficient, and the molecule that forms from the reaction of this boron trifluoride with ammonia then has the chemical formula of H3NBF3, and in this molecule the boron atom now has the octet of its electrons that satisfies its octet rule. So now if you can see, it has 2, 4, 6, and 8. This can also be a bond here. So here, in this situation, this did not have a full octet. It was electron deficient. It had fewer than 8 electrons, which made it actually very reactive towards reacting with molecules such as this ammonia. And ammonia had this lone pair of electrons here, just so ready to form a bond. And now through this reaction, it forms a compound that's more stable and has that octet of electrons satisfied. The second example of the exception to the octet rule is molecules where the central atom is surrounded by more than 8 electrons. For example, in a molecule such as sulfur hexafluoride, where you have 1 sulfur surrounded by 6 fluorines, the sulfur atom in the sulfur hexafluoride molecule has an overfilled octet. So if you count the number of electrons in sulfur, 2, 4, 6, 8, 10, 12, it actually has way too many electrons here. So this is another example of a molecule where it might not follow the octet rule. And then you can have molecules that have an odd number of electrons, such as this nitric oxide or this nitrogen dioxide. And these are relatively rare, and they're usually quite unstable and very, very reactive because they have an odd number of electrons. So if we around their, so if we can count the number of electrons here, 2, 4, 6, and 7. This nitrogen does not have its full 8. It has an odd number. Same with this one. If we count the number of electrons around this one, 2, 4, 6, 7. It's an odd number, and it's very, very unstable, very, very reactive. So this was just for your awareness to understand that there are certain situations that the octet rule does not apply, but typically the case is that yes, the octet rule holds for most of the atoms, the first 20 elements of the periodic table. Finally, there are some support questions for you to attempt and work through And at the end, you have these key questions. 1, 2, 3, and 4. So these questions are due by Sunday. I'll put down a reminder here that they are due Sunday. What's the date? Sunday the 26th. By midnight. So just make a note of that and make sure you work on these key questions and hand them in. They will be graded for marks. Okay. Thank you so much for your time. If you have any questions, please don't hesitate to ask me, get in touch with me. I will again post the recording and I will share the lesson with you on your Google Drive so you can look at it and review it on your own convenience. Okay. All right. Have a good night, everyone.
Thank you. Have a good night.
Thank you, Sasan.
Bye.
Bye.
Bye, Judy.